me know once.
Okay, welcome everybody. It's my pleasure to introduce the 22nd speaker of the Birational Geometry Seminar this year. The speaker is Peter McDonald from Simon Fraser University, who will speak about the Bianco-Scola theorem for pseudo-rational and Dubois singularities.
Cool. So thanks, Joaquin, for the invitation. This is a fun project, so I like getting the chance to speak about it. Please pop in with questions at any point, um, if you have them. Otherwise, I guess we can wait till the end. Um, but the Briançon-Skoda theorem is, I guess, now about a 50-year-old sort of thread of research in commutative algebraic geometry. And so for my goal for today is to give you a bit of the history first, before we jump into what our result is. And really the motto of the talk is the proof of what we proved was actually quite simple. So I'll be able to present essentially the whole proof in the talk today. Um, and so what the Briançon-Skoda theorem ultimately is it's a theorem about integral closure of ideals. And so I'm just going to start with a definition. So let's take our Noetherian. You don't actually need Noetherian for the definition, but well, I guess for this definition it's nice, but not for the general definition of integral closure. And let's take Y to be the normalized blowup of I. Um, and we'll just set I OY to be OY minus E. Um, then the integral closure of R is going to be an ideal, a larger ideal. And it's just given by essentially you're taking global sections of OY minus E. So in some sense, you can think of this as like you're extending the ideal up to Y. And then by taking global sections, you're essentially contracting it back down to R. Um, you do need to be a little bit careful. If R is not normal, you need to take the intersection back with R to make sure you don't get too much. Um, so a relatively clean definition. There's also an equational definition that'll pop up in an example later, I think. Um, and two remarks I want to make about this. So since this is a birational geometry seminar, um, one reason you might be interested in integral closures of ideals is that if you take any proper birational map of normal varieties, um, and let's just take D to be a Cartier divisor, an effective Cartier divisor on Y. Then if you take the push forward of OY minus D, this is a sheaf of integrally closed ideals on X. So in some sense, the way we define integral closure is essentially like how integrally closed ideals show up. Um, and so in particular, for example, the multiplier ideal is integrally closed. Um, the second remark is you can also think of this in terms of valuation. So it's not going to be super relevant for the talk today, but I think it's nice to see. So for simplicity, let's just have R be a domain. And we're going to consider basically all valuation rings over R living inside of its fraction field. Um, if you take, you can also realize the integral closure as the intersection over all these V of, okay, what do you want to do? Well, you want to essentially do the same thing. You want to extend the ideal to V. And the way we're going to extend the ideal to V is we're just going to tensor with R mod I. And then by taking this kernel of the map from R to V mod IV, you're going to get the contraction back to R. So you're essentially extending and contracting to all these valuation rings. And if you take the intersection over all of those, you get the integral closure. So again, not super relevant for today, but a nice way of, another way of thinking about integral closure. So the Briançon-Skoda theorem is due to Briançon and Skoda, who, depending on your knowledge of history, you might recognize are not algebraists, but are in fact analysts. Um, so what they showed, maybe one way of writing it, is if you take some ideal generated by, say, n elements inside of, let's just take like the power series ring and d variables, then what they showed is for all k greater than or equal to 1, if you take the integral closure of n plus k minus 1 I to that power, take the integral closure of that, that's going to be contained in I to the k. Um, I guess maybe like an aside over here. Uh, I is of course always contained in its integral closure. Um, Generally, it can be a lot bigger. And so one thing like algebraists in particular are interested in is, okay, if you have an operation that makes your ideals bigger, can you reverse the containment by powering up your ideal enough, essentially? Um, and I think this was motivated by a question that was floating around at the time of Mather. I'm not sure in particular what led Briançon and Skoda to tackle this problem. But the reason this became interesting for algebraists is, the statement as I've written it is purely algebraic. But the proof uses a result of Skoda um, in L2 analysis. And so at the time, that was, I think, particularly surprising that you could use analytic, or rather, you could have an algebraic statement, use analytic techniques to prove it, and then I think it was quite difficult for people to find an algebraic proof of this statement. And so there's a paper of Lippmann and Tessier, which I'll be citing at some point. Um, but they say in the introduction, like the lack of algebraic proof is certainly a challenge and perhaps even an insult or something along those lines. Um, and so luckily,
Scandal.
algebraists, oh yeah,
He says this is scandal.
a scandal, yeah. Um, so uh, it was not actually Lippmann and Tessier who proved the algebraic version, but we'll have something to say about them in a moment. But as soon as you have a result about, say, like a certain kind of power series ring, in this case over just the complex numbers, you might wonder if that result is true for general regular rings. Like, is it a characteristic dependent result? And that's actually going to be a theme today. It's also coming up with a characteristic independent perspective on a lot of this stuff. And so it turns out, yes, this is characteristic independent. So if you again take some ideal generated by n elements, now we're just going to look in some regular local ring of dimension d, and the same statement's going to hold. So you'll get used to and perhaps tired of seeing this. But for all k greater than or equal to 1, the integral closure of I to the n plus k minus 1 is contained in the integral closure of I to the k. So that's great. This talk is about
Can
singular
I ask
rings.
something? Do we know
Yes.
examples in which the equality holds for every k?
Oh, equality?
Yes.
Um, Not off the top of my head, but I would imagine people do know. Um,
Thank you.
Yeah, this was like pretty heavily studied for like 20 years, and then it kind of died off for a little bit. Um, so the talk today is going to be about singular rings. Essentially, as soon as you have a result about something that's smooth, you might wonder, okay, is there a broader class of singularities for which this result holds? And so before I jump into that, though, because again, this is a birational geometry seminar, I want to talk about sort of what the Skoda result that was used says in modern language, in particular in algebraic language. So this is sort of an aside. It's not really going to be relevant for the rest of the talk, but I think it will be interesting to this audience. So Skoda's theorem in modern algebraic language basically says that for all k greater than or equal to 1, and I want to make sure I don't get my numbers messed up, but it says that if you take here the multiplier ideal of I to the n plus k minus 1, that's contained in I to the k times the multiplier ideal of I. Oh, shoot, I made a typo. I think it should be n minus 1. Yeah, I have a typo in my notes, and I think this is what I meant to write. And so this immediately proves the Brianson-Skoda theorem because multiplier ideals, they're push forwards of things from a resolution. I guess, yeah, and you're regular, so you're definitely normal. And so, uh, and I guess I should say this is like in the setting of, say, a coordinate ring of a complex algebraic variety. Again, because Skoda's theorem was about, using L2 analysis. But right, we immediately get that the integral closure of I to the n plus k minus 1 is contained in that multiplier ideal. And then certainly the multiplier ideal is an ideal sheaf, and so is contained in your ring. And so the Brianson-Skoda theorem kind of just falls out of the statement as soon as you rephrase what Skoda proved in terms of multiplier ideals. And so in this same direction, there's two results I want to highlight. So Lippmann in 1993 wrote a paper called like adjoint ideals in regular local rings. And so when Lippmann defined this notion of an adjoint ideal, people later realized this is actually a multiplier ideal. And so Lippmann essentially like phrased Skoda's theorem algebraically. Um, I'm not the best historian, so it's hard for me to tell if at the time he was like aware that he had phrased Skoda's theorem algebraically. I would imagine he had some sense. Um, but and basically showed that it follows from, that's some stray, it follows from basically like a Grauert-Riemann-Schneider type vanishing for multiplier submodules. And in that same paper, Kutkovsky uses Kodaira vanishing to settle this for local rings that are essentially finite type over C. So again, of course, this result was known, but giving the algebraic proof was really the goal. No, I need to add a page. Why is it not letting me scroll? Oh, weird. I've never had this not infinitely scroll. How do I fix? Okay, apologies. I'm gonna have to jump to the next page. That was not my intention. Okay. So the other result I want to highlight is Ein and Lazarsfeld from 1999. So they give a global proof. Maybe I should say algebraic proof of Scotus theorem using Kawamata-Vivek vanishing. And they ultimately use Scotus theorem. The title of the paper is a geometric effective Nullstellensatz. Yeah, to get an effective Nullstellensatz. So Scotus theorem is upstream of the Bryanson-Skoda theorem. It implies it. It also can be used to get this geometric effective Nullstellensatz. And another big topic that people are interested in that sort of flows from Scotus theorem is like the study of symbolic powers and sort of similar containment type results for symbolic powers. And so in some sense, people in trying to tackle the Bryanson-Skoda theorem as you expand to singular rings, excuse me, we're expecting that some sort of like vanishing theorems or Cohen-Macaulayness would play a role in this. And essentially, what our result or our proof of what I'm going to tell you about later is that you don't need really any of these vanishing theorems. So in some sense, there's a way to do this just algebraically without using vanishing theorems. Um, so okay, so let's move on now to singular rings. I'll give you a definition. So again, the hope after Lippmann and Sathe's result is that there should be some characteristic independent statement of Bryanson-Skoda for singular rings. And so they actually needed to define, or rather the people who proved this needed to define a characteristic independent notion of singularities. So we're going to say that Rm, a local ring, has pseudo-rational singularities if R is normal, Cohen-Macaulay, analytically unramified, meaning its completion at the maximal ideal is reduced. And for all pi from Y to spec R, proper birational maps with Y normal and integral, we have that, okay. R is Cohen-Macaulay, so we look at its only local cohomology module. There's going to be a map from that to the local cohomology on R gamma YOY, so some complex of R modules that gives you the sheaf cohomology of OY. And we're going to ask that that map is injective. And so the goal of this, and the way you want to think about this is like a characteristic. And actually, maybe before I do that, it's a characteristic-free weakening of rational singularities. And so it turns out that this is actually equivalent to pseudo-rational singularities. And that's sort of what Lippmann and Tessier were going for. And it also encaptures, but is larger than the class of F-rational singularities, if you're interested in positive characteristic, or more recently, uh, the notion of BCM rational singularities um, in mixed characteristic. And so pseudo-rational is meant to sort of, again, in a characteristic-free way, encapsulate all these different singularity classes, whose definitions are very much characteristic independent. I wish I could figure out how to scroll. Don't know what the issue is. Okay. Oops. Okay, I'm going to move on to the next page, but if you need me to go back, please don't hesitate to ask. Okay. So the theorem and the motivation for this definition of Lippmann and Tessier from right about the same time as Lippmann and Sathe proved the Brillouin-Skoda theorem for regular rings, is that if you have, say, R m pseudo-rational of dimension d, and we take some ideal in our ring, then for all k greater than or equal to 1, we get a very similar looking containment. I to the d plus k minus 1 is contained in I to the k. And so this was great, but it was expected already at the time that this result was suboptimal. So of course you can have ideals generated by like arbitrarily many elements. So you can't expect the number of generators of your ideal to be bounded above by the dimension. But I have hid something from you a little bit, which is you can basically always find what's called a minimal reduction of your ideal, which is a smaller ideal that has the same integral closure generated by at most d elements. Um, so really, when I'm showing you these theorems, it's easier to state them for an n-generated ideal rather than telling you what analytic spread is. But you can always guarantee in some sense that that n is less than or equal to d. Um, and people really expected that. And so that was a big, right, this was the first algebraic proof of the Brillouin-Skoda theorem, and then this result for singular rings came out right about the same time. And so people really spent a while trying to like tackle this singular result and see if they could optimize it. And really, there was a lot of work. I'm gonna not tell you all about it. I do want to highlight really what is probably like the state of the art. Um, up until now, which is a result of Aberbach and Hunicke from 2001, which using tight closure techniques, so this is going to be a positive characteristic result, I don't need the dimension of the ring anymore because they got rid of that. But if you have an excellent F-rational ring and you take some ideal generated by n elements, they gave what you are now, again, perhaps tired of seeing, but the optimal containment, which is I to the n plus k minus 1, the integral closure of that's contained in I to the k. And so that's great in positive characteristic. So, and what this actually does is using reduction mod p, this settles the Brillouin-Skoda theorem in ker 0, meaning, say, for R containing Q with rational singularities, which again are equivalent to being pseudo-rational or having pseudo-rational singularities. So basically, the state of the art was this result. So there are examples of rings with singular or with pseudo-rational singularities that aren't F-rational. So there was still a little bit of a gap in positive characteristic. Um, there was no expectation that these techniques would have any purchase in mixed characteristic. There is some work of Heitman and mixed characteristic that gave some results. But the theory of singularities and mixed characteristic is still very much like an ongoing development. The past 10 years have yielded a lot of understanding. So, you might not expect there to have been much to say about singularities and mixed characteristic back in the early 2000s, based on what we know now. So again, this was really the state of the art until, oops, I don't want to change the page yet. This is very strange. I don't know what's happening here. Okay. So I want to give one last definition before I present our main theorem. So it's going to be a new class of singularities. So we're going to just require that R be reduced. And we're going to say that that reduced ring is a birational derived splinter if for all maps from Y to spec R proper birational, there's always a natural map from R to R gamma Y O Y, this complex that showed up before. This is a map in the derived category of R modules. These are both bounded complexes, so we might as well throw a bounded on there. And so the notion of splitting just means that there's a left inverse to the map. So some map back such that the composition is the identity on R. And this is where it's kind of annoying that my iPad got messed up with its page thing. I'm going to go back quickly to this diagram I drew here. And important for the context of this talk is that birational, derived splinters offer a broader class of singularities than pseudo-rational, at least in positive and mixed characteristics. So it turns out you get nothing new in characteristic 0, which is fine because, that's the case we understand for this theorem at least. But I don't really have room to put this underneath because of the scrolling issue, but these are not necessarily Cohen-Macaulay in positive or mixed characteristic. So it really is a larger class in positive and mixed characteristic. And in particular, Cohen-Macaulayness is not a consequence of being a birational derived splinter. And like I alluded to before, people sort of thought that vanishing theorems and maybe Cohen-Macaulayness of your singularities was going to play a role in the proof of the Briançon-Skoda theorem. And what we ultimately found is that it does not. Okay. So I'm now ready to state our results. And now that I'm realizing my slides are sort of weirdly cut off, I can do that here. Okay. So like I said, this is joint work with Linchuan Ma, Rebecca R.G., and Carl Schweed. It was on the archive last year, but it's now officially accepted. So I can say 26, I guess, instead of 25. And you can probably already guess the statement. So we're going to have our ring be a birational derived splinter, and we're going to have I be an ideal. And our result is that the optimal Bryanson-Skoda statement that the integral closure of I to the n plus k minus 1 is contained in I to the k holds for all k greater than or equal to 1. So in particular, this generalizes Hünicke-Aberbach or Aberbach-Hünicke. It sort of gives a full understanding and mixed characteristic of what's going on here. And like I said, the proof is really quite simple, so I'm going to show it to you now. So let's just do k equals 1 here. It's not an induction proof. I'll explain what happens for k greater than 1 later. It's the same proof, essentially. You just swap out an object that I'm going to give you. And so let's take y to spec r to be the normalized blow up of I. And we'll again set I-O-Y to be O-Y minus E. And we're going to consider the Cazul complex of the F1 to Fn on OY. So, right, I'll maybe denote this by KF OY. And we know it's got this nice symmetric structure where maps are given by sort of multiplication by the Fs. And the key, and this is something that people knew in other contexts, is that inside of this, there sits an exact subcomplex. So I'm just going to call it B for today. I might need a little more space, so I'll label it afterwards. But what that complex is going to look like is you're going to successively twist by one more copy of E each time. And I'll call this B. And the argument that this complex is exact is really not so bad. In some sense, you can think of it as, okay, what's happening? Oop, a little bit like what's happening in this last map right here? Well, right, I'm multiplying each of these summands by one of the FIs. That generates the whole ideal. And in fact, is surjective, right, because I've twisted by one more copy of my exceptional divisor. Another way you could think of this complex is coming from the Cazul complex on, say, you specialize to one of the charts corresponding to one of the FIs. What you've basically done when you take the Cazul complex on those generators is you're resolving the trivial ideal, right? Because if you have Fi as a generator, when you invert Fi, okay, now 1 is in your ideal, you get a trivial ideal. And so the Cazul complex on a trivial ideal is always going to be exact, right? If you have a unit in your sequence. And so that tells you that this complex is exact. And then it, very clearly sits inside the Cazul complex because these are just ideal sheaves. So really nothing fancy going on here. And then what we can do is I can basically chop off the degree 0 piece of B. So there's a map from that degree 0 piece into B. And then, right, B sits inside of this Kazul complex. And the key is that this map is 0 in dBy, right? It factors through an exact complex, and exact complexes are just 0 in the derived category. And this is basically all we need. So what are we going to do? Well, we want to make a statement about ideals in our ring. So we should get back to the derived category in R. So we're going to apply R gamma Y to this. And I'll cut out B now because we know that we don't really need to bring that along for the ride. And the Kazoo complex is nice and functorial, and so it turns out that that's the same as looking at the Kazoo complex on R gamma Y OY. And so now we have this map from R gamma Y OY minus NE to the Kazoo complex on R gamma Y OY. That map is 0. And if I take H0, right, if my map of complexes is 0, clearly the map on homology or cohomology is 0. And this is where you might start to see how this is going to tell us something about integral closures. So if I were to flip back to the first page, right, I wrote this down when talking about the integral closure of an ideal in my ring. And so what can I do? Well, again, we're not assuming that our ring is normal. So I do want to intersect back down to R, and that's going to give me the integral closure of I to the n. And there's always a map from R to R gamma Y O Y. And so that induces a map on the Kazoo complexes as well. And the important thing is that and that's not the Kazoo complex because I've now taken zeroth homology. And the important thing is that this map is actually a split injection. Because R is a birational derived splinter. And so why is that nice? Well, what is H0 of the Kazoo complex? It's just your ideal, or R mod your ideal. And so the map on zeroth cohomology, at least after we intersect back down to R, actually factors through R mod I. And because the second map is a split injection, that forces the first map to be 0. And we at least have the Bryanson-Skoda theorem for k equals 1. And so the proof for k greater than 1 is, like I said, almost exactly the same. What you're going to do is you're going to replace this Kazul complex with something. I'm just going to write down notation, not really saying anything. But you're going to replace it with something called LKF. And this is the Buchsbaum-Eisenbud complex, or equivalently, or up to isomorphism of complexes, the Egan-Northcott complex. And how does it, what does it look like? Why is the proof exactly the same? Well, the key things here were basically that this was a length n, or I guess n, degree 0 to n complex of free things. I'm indexing homologically. And the maps between those free things are just linear in your generators. So what happens when you move to the Buchsbaum-Eisenberg complex? Well, the length is the same. It's still a length n complex of free things. The maps out here are all going to be linear in the FIs. So you'll pick up n minus 1 here. And then the last map, basically this is going to resolve R mod I to the k if you're in like a complete intersection situation. And so this last map is going to be multiplication by the k-fold products. So you have n minus 1 linear things plus a k-fold product, so n plus k minus 1. And so the exact same proof gives you the stronger statement. But today I don't want to tell you too much about that complex, so I won't dive into it. But trust me that it's the same argument. Okay, so that's our proof. I want to give a quick remark about the Dubois setting without necessarily telling you what Dubois singularities are. So the key for the next 7 minutes is just that Dubois is a slightly larger class of singularities than rational singularities. It's also defined in a similar way in the sense of a map to a complex being an isomorphism or a quasi-isomorphism. And so what we can do is we can go back to the key step in the proof, which didn't use that we were a birational derived splinter at all. And again, I'll stick to the k equals 1 case here. So the key of our proof is that this map from OY minus NE to the Kazul complex on OY is 0. So unfortunately, I'm running up against the page limit. But what I'm going to do is I'm going to twist by OY minus E. Oops. Okay. And so, right, nothing revolutionary happening here. We still have a 0 map. And I'm going to, again, now take R gamma YOY, or I guess R gamma Y blank. My map stays 0. And I'm going to need to introduce some notation here. And so I'm going to consider F. So Y is still my normalized blow up of my ideal. F is going to be the reduced preimage of the vanishing side of the radical of my ideal. So this is NY. And so maybe I'll draw a little picture just to help orient ourselves. And what I'm going to consider is there's an exact triangle in DBR. So from the just exact sequence corresponding to F living inside of Y, we definitely have a map from R gamma Y OY to R gamma F OF. And we also have a map right, from coming from this map here from R mod the radical of I to that same deal. And when you're in the derived category of a ring or coherent sheaves or anything, it's a triangulated category. So there's always a way to complete this map to an exact triangle. And we're just going to call this thing on the left D sub I. It's a complex. I don't really need to know what exactly it looks like. But the important thing is that there is a map from R gamma Y OY twisted by minus E. That is basically just coming from the fact that, right, OA minus E is going to live inside the ideal sheaf. Defining F. Essentially is where that map is coming from. And so if I now take, let me just copy this. I take this zero map here. What I can do is I can just replace, right, by further mapping to DI, I can replace that R gamma Y, OY minus E by mapping to this DI. And there's also a natural map from R to this thing. If you just kind of work out the diagrams, it sort of falls into place. And the key is that when R is Dubois, or has Dubois singularities, this is actually a split injection. And for maybe people who have seen Dubois singularities before, the key, it's a very simple proof if you've seen them before, but if you haven't seen them, there's a lot of background. But the idea is that the definition of Dubois singularities is that the map from R to what's called the zeroth graded piece of the Deligne-Dubois complex is an isomorphism in the derived category. And the key is that that map actually factors through this DI thing. This comes from like a triangle and like the early work of Steenbrink on Dubois singularities. So if you have seen them before, it's like, okay, this is all you really need. And the key is, okay, well, this factorization is literally giving you, the splitting from R to DI that you want. And so that forces a split injection here. And so,
sorry, can I ask a quick question? How
Yeah.
do you get a map from R to DI?
It basically comes from the fact that I think R maps, if I remember correctly, it maps here, and it sort of essentially, there's not really kernels here, but yeah,
Yeah,
it
no.
therefore like lifts.
Yeah. Thank you so much.
Yeah. And so from that, and maybe I won't go through the whole process because I just realized it's 1 minute after I wanted to finish. But if you just take zeroth cohomology, you get I now to the n plus 1. The integral closure of that is contained in I. And more generally, if you replace the Kazoo complex with this Egan Northcott Buxbaum Eisenbug complex, you get I to the n plus k. The integral closure that's contained in I to the k. And there is a result of Lexi Wheeler and Wenliang Zhang from 2025 that actually recovered this in positive characteristic. And it turns out that, without going into too much detail, this splitting criterion that you need right here holds for F pure singularities in positive characteristic, or Cohen-Macaulay and F injective singularities as well, and potentially F injective singularities, but I don't think we know that either way. Okay, I will stop there.
Thank you for the very nice talk. Are there any questions from the audience?